Hey guys, how you doing? It's Coach Scott. Let's go to our third little video on periodic properties, periodic table, the periodic model. Now we're going to talk more about electron configurations and stability. Okay. So, when you study an element, scientists notice that when they're in the same situation, some elements reacted while others did not. So the elements that did not react, we labeled those stable because they didn't change very easily. And when they grouped these elements together, they formed a pattern. When they grouped them periodically, periodic table, they formed a pattern. So now we know more about quantum mechanics, right? We know the quantum model, and we know that this difference in stability is due to their electronic configurations. So, look at these two elements, and knowing what you know now, which of these two elements is going to be more stable? Argon, 1s2, 2s2, 2p6, 3s2, 3p6, totally filled, third energy level, or zinc, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. Think about it. Pause, discuss it. And of course, we know that argon is more stable than zinc. All right, now we're going to find out why. So, we have different stability levels, right? Different varying levels of stability, and we've got three categories we put them on. The most stable atoms have completely full energy levels, right? And what are those? The noble gases. That's why they're inert, because they're pretty much can't react until you get really, really fat. We're not going to talk too much about that this year. Next are those with full sublevels. So a full S level is going to be more stable than a not full S level. A full D level is going to be more full than some of the D's that aren't full, right? When there's open electrons there. So the full F's are going to be more stable than the ones that aren't full. And of course, the full P's, those are the inert, the noble gases, they're as stable as you can get. So the next level, okay, are the half-full sublevels, okay? Now, they're pretty stable, but they're not as stable as the elements with the full energy levels or the full sublevels. So there we're talking about the D5s. So they have one electron in each of those orbitals, right? And of course the F7s, there's one electron in each of those 7 orbitals. So they're got an electron there. They're not totally full yet, but they're happy. And of course P3s, they're not listed there, but they're a little bit more stable. Let's see if I can draw this one. They're more stable. No, I'm just moving things around. Yeah, maybe there we go. The P3s, they're more stable than like the P4. Right? So, where the exceptions occur, they don't really occur in the p orbitals because they're pretty high energy, are in the D's and the F's. So if I have a D4 or D9, that's where the exceptions are going to occur. All right. Or if we're looking at the F's, 1, 2, 3, 4, 5, 6, the 6s and the 9s on the F are on the 6s and the 13 are on the F. That's where they can get a little crazy. So let's take a quick test of what we know. So the elements in the periodic table that have completely filled shells or subshells are referred to as what? Take a break. Noble gases. Their shells are filled. They're happy. So alkaline earth metals are more stable than alkaline metals because why? Take a break. They have a full S subshell. Okay. So B. They've got the S2 that's filled up, which is more stable than the alkali metals, which are the S1s. The elements in the periodic table which lack one electron from a filled S or a P subshell, okay, are referred to as what? Okay, there's one electron to have be totally filled. Take a break. See, think. Those would be the halogens. Okay, so they got the S field, the S2, then they have one electron away from being a noble gas configuration. So here's some of the exceptions. Let's look at chromium. Chromium, element number 24, is right there on the periodic table. All right, so we would expect it, the configuration to be, well, the shorthand, argon, that's argon right there, 4s2, 3d4. What we find is it's not 4s2, 3d4, it's 4s1, 3d5. So what happens is this actually costs less energy to take one electron from the s orbital and put it with a d orbital to make it more filled. So there'll be one there, then 5 there. So you filled up that sublevel, all right? That gives it more stability. Now let's think, wow, that totally goes against everything we learned, Coach Scott. Well, let's look back at our little chart. Remember this? If you look, the 4s2, or the 4s energy level, is pretty close to the 3d. All right. If you look at how the D's and the F's are, all right, they're pretty close. All right. So that doesn't take a lot more energy to move that electron from the s orbital. Now it leaves it half full, but they'll put it to the d orbital or to the f orbital, and that will cause it to be half full, which makes it sort of happier and more stable than if it just stayed the same. So this is a good analogy. It's like borrowing a cup of sugar from a neighbor to make your cookies or whatever. All right. So our exceptions are going to be where? Look at copper. It's one away from having a completely full D subshell. So what does it do? It borrows the electron from the S subshell, and it'll make that full, complete orbital. It's happy. All right. So the exceptions are going to be here, okay, and there, in the D level, right? So that makes it happy. And they'll borrow them from the S orbital, and it'll be half full, and it'll be happy. So let's look at copper. Again, if we were to do copper, it would be argon. Copper is element number 29. It's one away from being totally full. Argon brackets, 4s2, 3d9 is what we would normally write. 4s2, 3d9. But now we know that there'll be an exception, and the correct configuration for that would be argon 4s1, 3d10. That will be D. Okay. What would the shorthand configuration be for silver? Again, silver is right below copper. It's going to be krypton. And again, now that we know that the D subshell will borrow that electron from the S, that's going to be D also. D also. What would the shorthand configuration be for molybdenum, MO? Now that's element 42. It's got, if we were to actually like do what we knew beforehand, we'd call that krypton, 5s2, 3d4. But now we know we want that one orbital filled up in the d level, so they'll borrow from 5s1. That's going to be krypton C, 5s1, 3d, 4d5. Now, for the most part, I'm not going to bug you on the exceptions, but the exceptions make life interesting. So hopefully that answered some of you guys' question that you may have had. I know this is a short video. We'll be collaborating on some questions. And so this is Coach Scott saying ta-ta for now, and have a great Red Devil day.